So before we do, I have to ask, I've been getting a few emails from you guys regarding the past homework, 27. How many of you guys in this audience forgot to do it or wasn't clear about the due dates? Just a handful of you. All right, so I'm counting 3, 4, 5 total, 6, 7. So 7 total. All right, so just because I allowed one person to do it before I knew what the due date was, it's okay. You guys can fist bump. That's fine. I'm going to let the rest of you guys do it. Just send me an email as soon as class is over, and I'll extend the due date for you guys until midnight today. But please don't let that happen again. Those deadlines, well, I mean, if I start moving, pretty soon they won't mean anything. But yeah, so from now on, just bear in mind what the due dates are, so there's no confusion. Usually, I'll try to give one week time to do the assignments. 28's been assigned. It's due, I believe, next Wednesday or next Thursday, something like that. Next Thursday, yeah. So you guys have another week for that. Also, in terms of help, do you guys remember Junchen from for the first half? So there's another guy named Yao Dong, really nice guy, smart guy. He's taking over for Junchen for the second half, and I spoke to him, and he's going to have help desk sessions right after lecture from 2 to 5, so Monday, Wednesday, Friday, in the first floor help desk room. You guys know where that is? Yeah, first floor. Yeah, first floor in this building over there. So it's in the hallway. If you're going down there, it's across from the offices. You can't miss it. So he's an invaluable resource. I would highly encourage you guys to go there and seek help with homework if you need it. Last year, me and the other lecturer used to run the help desk sessions, and we had a lot of students. And I've seen that the students that come there generally tend to do a lot better on the exams, just because they know what the problems are, they know what they can expect. Go there and then seek help from him for all the homework. If you guys can't make that time, I understand some of you may have recitations during that time. He also agreed to see you guys during his office, or in his office whenever he's there. Apparently he's going to be there most of the time, and I believe that's 4th floor, 460, this building. Right, so that's another resource you guys can use. Another thing is I misspoke on Wednesday when I said my office was 418. It's actually 466. I was there in 418 on Thursday for the office hours, but no one showed up, so that apparently wasn't a problem. But yeah, it's 466. So from that time, but all the homework, try to go to see either the TAs or Yao Dong in the help desk session. And I mean, the way I'm trying to structure this is that during lecture, I want to give demos so you guys can actually see what all this physics means, because obviously seeing is believing. I want to inspire the theory behind it, how it's all come about, and I mean also give some examples, like numerical examples and real life examples that sort of put a face to all this. But I want to have the recitation times more for problem solving and all that. I mean, I even gave the TAs more leniency. They can give you quizzes if they want. If not, then they can just do problems. That's fine with me, but I still require a quiz grade from them. So as long as I get a quiz grade in the end, I don't care if they give you 10 quizzes, 20 quizzes, doesn't matter to me. So use their time effectively. So it will be really helpful if you guys actually attempt the homework before going in. I don't want to get complaints from the TAs that you guys are just asking them how to solve problems from homework. That's not going to help you. Attempt them and go there with specific questions, and that'll be a lot more effective use of your time and the TA's times. So are we good on that? All right. I blitzed through Ampere's law on Wednesday, so I realized there may be some confusions when I was going back and looking at it, so we'll do a quick review of that, and hopefully it'll clarify any holes in your knowledge that may be, and we'll go from there. All right. So I mentioned we started off with Biot-Savart law in the beginning, right? And then we calculated the magnetic field on a current carrying conductor or wire, and we were able to extrapolate that. And then on Wednesday we even came up with the same answer using Ampere's law, right? So what did we have? We had, once we erase the board, right? So we had standard current carrying conductor. We're looking at a cross section of this, and I'm saying current is coming out of here of the board, right? Now if I take a surface around it, boundary for instance, something that encloses this, right? I want to find what the magnetic field is around there. So I mean, granted, now this is uniform current going through, then I would have uniform magnetic field, and that's dictated by the right hand rule, right? I would know what that's going to look like. So if current's coming through here, I know magnetic field is going around, so it's tangential to this. At this point it's like this point it's like this, and so on, right? Wait. Oh yeah, you're right, it's the other way. So this way, right? Yeah. So that's how the magnetic field will look like, right? Now what we also said was, okay, we have this loop we're looking at, how about we walk around that loop and integrate it, right? So let's take a closed loop integral of this, right? Little circle means closed loop integral of this circle, right? And if my magnetic field is this way, let's say my dl, I want to walk around in the same direction as the magnetic field, so I'm going to say my dl is in the same direction, right? Obviously I have this loop, so I'm going to be carving this up into small dl elements all throughout, and I basically integrate over that. So I would have b dot dl here, and this, because it's a constant magnetic field, and because dl and b are parallel here, right, which means that the dot product between these is just b dl, right? And then when I integrate over the whole thing, I just get the circumference of the circle, assuming that my circle is radius r. I would get b times 2 pi r, right? Now before we did that, last time we saw that the magnetic field due to that current carrying conductor at some distance r was b equals mu naught I over 2 pi r, right? So if I were to equate these two, and if I was to plug this in there, I have, or if I multiply this by 2 pi r, I get b times 2 pi r equals mu naught I, right? So effectively this is equal to mu naught I. And from here I can say, if I divide out by this 2 pi r, I get back the same thing, b equals mu naught I over 2 pi r, right? But effectively this is what I'm looking at. Now I'm saying that this integral, this closed circle integral here, is equal to mu naught I, right? So from here I can say closed loop integral of b dot dl equals mu naught I, right? So this we called Ampere's law. So far we know two Maxwell's equations, and this is almost the third one, right? Ampere's law is one of Maxwell's equations, but this is not in its correct form yet, and later on in the course we'll go back to this and amend it to correct it. But as of now, we sort of have like 2.5 Maxwell's equations. So we're almost done with the course. One and a half more equations and we're done. Close the book. So I mentioned over here we start off with a closed circle, but it doesn't have to be a circle because as long as you're uniquely defining this, it can be anything. Also, before I forget, most of the books have the notation, or not just books, but pretty much everyone says, okay, Ampere's law at this stage, you have B dot dl equals mu naught I enclosed, right? You're saying the current is enclosed, but what exactly does that mean? How can you enclose that current? So that is sort of poorly defined in my opinion, because what we're looking at there, you have some, let's say, current carrying conductor that's carrying current through. You put a surface on it, right? It's an open surface. How can you enclose something with an open surface, right? That's not really very intuitive. So if you want to think about this current that's enclosed is actually current that's penetrating through that surface, right? Does that make sense? So we have our surface, open surface that we attach to this, and then as long as it's penetrating through, that's the current we're looking at. So you can actually think of this as current that's penetrating, not enclosed. So it's not exactly intuitive to think of something that's enclosed by an open surface, by something open. So in Gauss's law, when you had your spheres, Gaussian spheres, and all that, you're actually enclosing the charge within that sphere, so that made sense. With this, you don't actually have a closed surface, so you can't really enclose this. But we'll get to that in a bit. So we have our Ampere's law now. And as I mentioned, it doesn't have to be a circle. This can be just about anything. It could be that surface, and I have my current going in there. And let's say some radius r. I could have my B tangential to the surface, and my dl is also along this surface, right? As long as I can integrate that, I'm good. But generally, you want to pick, yes? This is usually from the center of the wire. But I mean, in this case, R is sort of meaningless because you can't really integrate that over. Yeah, but you go from the center of the wire. Yeah. So you want to pick a surface or your path that you can easily integrate over. And the easiest ones to do here are a circle, right? The circumference of that. And another one we'll look at today is a rectangle of a kind. Right? So for a rectangle, you can divide them up into segments, do line integrals for that, and you're done. But something for some contoured shape like this, not so easy. Now, when you attach a surface to this, the easiest surface to attach to this is going to be a flat one. Right? You have a flat surface, you know exactly where it's penetrating from, and you're done. But in principle, as long as it's closed, it's attached to this, it's an open surface, it could be just about any surface. You could think, if you want to think of it this way, a hat. Some of you have a hat on, right? So think of that bottom rim as the path you're integrating over, and that top part, that's your surface, right? And if you have a wire going through there, I don't know why you would have a wire going through a hat, but let's say you do, it's still a surface that's properly defined, and you can do that. Now, when you have currents, let's going from here. Let's say I have a current going in here, coming out here. Let's say my I1, and let's say I have another current coming inside this way. This is my I2, right? Now, by convention, this doesn't always have to be the case. By convention, let's say if we're going through this, looking at it from the left side, if we're going through this surface clockwise, right? Right-hand rule dictates whether the currents going in or out are positive or negative. So if I'm looking from this side, this is my surface, I have a current going in, right? I'm integrating clockwise, so whatever's going in, I'll say that's positive. And whatever's coming out of that surface, I'll say is negative. And that's just convention to keep proper bookkeeping. As long as you're consistent all the way through, it shouldn't matter, but it's better to stick to the conventions. So with this, now if you're looking at it from that side clockwise, you have I1 in this case is positive, and I2 is negative, right? And if you were to march the other way around, so if your DL was the opposing direction, if your DL is going this way, right? If you're going counterclockwise, then I1 would be negative, and I2 would be positive, right? Make sense? So let's go over how we solve these problems again. So first, you pick a closed loop, right? So let's write this down. So first, you pick a closed loop. Right? Any kind of loop is allowed. Any surface, any type of shape is allowed as long as you can integrate it. And then you choose a surface to attach to it. Right? And I mean, it has to be. It doesn't have to be a flat surface, but it does have to be an open surface. And the direction of travel, so how you define your DL to be, that's free to you. You can choose whatever you want. You can simplify it and say, okay, now I'm going to do it so that my current is positive. That's fine. Or if you want to say, okay, I'm going to choose my DL so that my current is negative. That's also fine. Just as long as you're consistent all the way through, you're good. And use the right, once you pick your DL, so you choose direction. Right? And once you do that, use your right hand rule. From here, you use your right hand rule and pick and you arrive at the proper sign for the current, and then you integrate and then you go about. Right? Doesn't seem too complicated, right? So it's almost like Gauss's law. You just take that closed boundary surface and make it a flat one, and you go through it. Right? So it's not too bad. Let's do an example. But we're a bit ahead of schedule, so we might actually get to go home early today. Or you guys get to go home, might get to go home early. Might. All right, so I think this is where we left off at the end of last lecture. So now let's do an example. So what Ampere's law allows us to do, that's something that is really difficult to do with Biot-Savart law, is that you can calculate the magnetic field both inside and outside a conductor. So for Biot-Savart law, you had to have, you were calculating stuff outside a conductor. For this, you can do both. And so let's take a wire, right? And some radius r. Oh, one more thing. So we have our Ampere's law states that we have B dot dl equals mu naught I enclosed, right? And for our Biot-Savart law, we had dB. What do we have? Right, mu naught I over 4 pi dl cross r hat over r squared. Now this dl is different from this dl. Totally different, so don't get those two confused. What this dl refers to is a small element of the wire, right? That's your dl. That's your dl for this one. What the dl here refers to is your path of integration, that you walk around, of the path you choose. So these two DLs are fundamentally different, so don't get those two confused. Right, so we have our current carrying conductor, radius r, and let's say we have current coming in this way. Right, so I want to find the magnetic field everywhere. How do I do it? Everywhere, inside and outside the conductor. Yes. So first, shall we do outside or inside? Outside. Outside is a bit easier, and I think you guys know why, right? Because inside you have to pick a, or not pick, but find the ratio of current that goes through the surface, all that. So let's do outside first. So let's redraw our diagram. We have our conductor here, currents coming out of here, I, right? I'll pick my surface to be out here. Now I said the radius of this conductor is radius capital R, and I want to find the magnetic field at some radius small r, right? So the first case, essentially what I'm looking at, is the case where small r is larger than big R. So we have our cross section here. We picked our loop, right? Now we want to pick our direction of dl. So I'm saying the current is coming out this way, so I want my current to be positive. So which way should my dl go? Counterclockwise, right? So I want to pick my dl to be in this direction. And if my current is coming out this way, which way is my magnetic field going? It's also counterclockwise, right? So my magnetic field is something like this, right? Everyone good on this? Okay. Now, because these two are in the same direction of travel, when I take my b dot dl, it's going to be a positive answer. If they're opposing, then I have to basically stick a negative in front of it. Right, so that's another way you can think about it. If you were to pick the other direction of dl, then yeah, your current, by convention would have a different sign. Yes. It's up to you. I mean, you're free to do that. It's up to you how you want to solve the problem. But there are some methods that are easier than others to solve, and I mean, yeah, you can do more difficult ones. Also, it makes your exams more interesting to grade if you do pick the more difficult paths. So. What's that? I give points to the needy, not the greedy. So if you pick the more difficult path and you're able to successfully complete it, then obviously it shows that you don't really need those extra points. We'll see. Well, I mean, I'm not out to get you guys, so you guys will get the grades you earn. All right, so we picked the direction of dl. I know my magnetic field direction. Now let's go through and write our Ampere's law and solve for this. So Ampere's law states I have a closed loop. B dot dl equals mu naught I and closed. Right? So I know what this is going to be. B is a constant magnetic field here. I mean, these two are parallel, so the dot product between these two is going to be b dl. Integrate that over a circle, I get b times 2 pi r. Right? You guys have done this thousands of times in math class here. So you get b times 2 pi r equals mu naught I and closed. So again, this is trivial integral, and from here, whatever I enclose is all in there, so it's simply just I. So b is going to be mu naught I over 2 pi r. Again, the same answer we got using that we showed before. Same answer we got using Biot-Savart law, right? And it's not surprising. I mean, they're both the same conditions, and you expect to get the same answer. So, oh, another thing. So last year for my exams, I actually got complaints that they were too easy. I actually did. I can show you the evaluations. They actually complained that it was too easy. I'm just giving you the facts here. I mean, I'm not making it up. And actually, it sort of was upsetting because I gave a practice exam. You guys all want practice exams. So I said, okay, fine. I'll take my time to make the practice exam. Came in on a Saturday, went through the practice exam for whoever showed up, and about 90% of the exam was almost verbatim the practice exam, and the average was still a 50%. So you can imagine how I feel when I go through all that time and you guys don't take the time to at least look at what I give you or tell you guys to look at. So I mean, I'm obviously not going to repeat the same thing. I'm not going to give you guys a practice exam and make it verbatim the same for the exam, because I learned my lesson. So look, we're all humans. We pick the path of least resistance, just like all these currents. So. All right, so now we finished the magnetic field when R is larger than big R, right? This is the first case we looked at. So now the second case we need to look at is when R, small r, is smaller than big R. So we're looking at something like this. So I have my conductor like this, and my path I'm looking at, my surface, is somewhere here. So this is my small r. Obviously, my current is still coming out of the board, and this is my large r. Right? Okay, so we write out our Ampere's law again. Integral b dot dl equals mu naught I enclosed. Okay, this is simple again. This is simply going to be b times 2 pi r equals mu naught I enclosed. So what is I enclosed now? I mean, it's uniform density current. So I'm telling you it's uniform current density. So it doesn't change with radius or anything like that. So how do I get my I enclosed here? Yeah, and the pi's cancel out, so I get small r squared over big R squared times I, right? Does everyone see how he got that? Okay, let's go over that. So we're looking at, let's take our surface here, our full conductor, right? What's the area of this? So I'm assuming that the current density is uniform through this, which means that at any given point I have the same amount of current as any other point in that cross section, right? So what is my area for this, if this is big R? Pi r squared, right? So I have area of pi r squared. Now, I'm not looking at the whole thing though. What I'm looking at, the region, is part of this, right? It's small r part of this. So the region, the area I'm looking at, is in fact pi small r squared. So it's a ratio of what I know, of what I'm looking at with what I have. So what I do is I get pi small r squared over pi big R squared. Right? That gives me the ratio of this area, and times I gives me the ratio of current that's enclosed or penetrating my surface here. Right? Is it more clear now? Any questions on this? No questions? You guys are experts now? All right, so good enough. All right, so my I enclosed here is small r squared over big R squared times I. Right? So, and of course this comes down here, so I have b times 2 pi r. I'm solving for b here, so b equals I small r squared over big R squared times 2 pi. And the r's cancel out here, so I get IR over 2 pi r. And this is for the case where small r is smaller than big R. if I look at this solution here for the case where it's outside the conductor, my magnetic field, yes. Oh yeah. Right, right. Thank you. So everything else good, right? Right. So over here I have 1 over r dependence for the case where it's outside the conductor, right? So it says that when it's outside the conductor, outside the wire, my magnetic field falls off as a function of 1 over r, right? Over here I have a linear dependence on r, which means that as r goes up, my magnetic field goes up proportionally, linearly. So if I was to plot this, we love plots, don't we? So if I was to plot this, put this up. All right, so I have my magnetic field there. So let's look at this plot. It's going to be my magnetic field as a function of r. So this is my magnetic field here, and this is my distance from the origin, if you will. So in the beginning, at the origin, I have to use that first one, right? When r is 0, my magnetic field is 0. And it's going to go up linearly until r is the same as big R, right? So it's going to go up until it's big R, at which point that thing takes over, right? We're looking at the field outside the conductor, and that thing falls off as 1 over r, so we get something like this, right? And obviously that's the maximum magnetic field that's on the surface, right? Now, if I plug in big R to that and big R to this, I should get the same solution. So that's known as boundary condition matching. So those two have to be the same, unless there's some sort of discontinuity or some weird problem, interesting problem. So in that case, if I plug in big R for the small one, I get mu naught I over 2 pi big R, right? In that one, if I plug in big R, I get mu naught I big R over 2 pi big R squared. This goes away, so I get the same solution here. So these two match up, and that's my maximum point. That's mu naught I over 2 pi R. Right, and this is 0. Make sense? Right. So again, these two are very different results, but they have to agree if you're looking at the same point. So on the surface, right, those two have to agree. All right. Let's look at one of the applications for this. Actually, before we do that, let me do a demo. So we've been discussing magnetic field lines and all that, but like I said, seeing is believing. So let's see if we can set it up. All right. Okay, works. All right, so here I have magnets, and some of them have iron filings in them, but they're just magnets placed throughout. Right? So I'll put this on here so you guys can see it. Right, so that's good enough. Some light. All right, so if I was to, these are just iron filings. So what do you think is going to happen when I put the iron filings on the magnets? form lines. Now, as you would expect, now if I'll have north and south poles, and they'll form lines around them. So let me put right. So you guys can see now I have the magnet here, and then I got lines that are coming around, as you would expect. So the same thing here. So you can see a bit wider lines here that are formed by this. All right, good stuff. All right, just show you guys I'm not just BSing all this lines malarkey. All right, so let's look at something called solenoids. Have you guys heard of what solenoids are? Some of you guys have heard of them. You guys haven't gone over it in this class yet, right? All right. So for those of you who haven't heard what a solenoid is, think of a slinky. Essentially a slinky with current going through it. That's really it. I mean, it's just coils, right? You have coils that are going around, and you can have multiple coil, like loops on top of loops on top of loops, depending on how complex it is. But essentially the simplest form of a solenoid is essentially a slinky with current going through it. So, and these have interesting properties, and of course with interesting properties comes interesting uses. And if something has interesting properties but is absolutely useless, yeah, you can pay some theorists to study it all you want, but we're just pouring money into it. Do you guys watch Futurama, or have you heard of Futurama? All right, in one of the episodes, I think it was Farnsworth or someone else was describing how something that they built, and it was basically on grant money and dreams of graduate students. I think it was basically burning grant money to get power for some accelerator he was doing. It's a very clever show. So, as I mentioned, you have solenoids. Right? So you have something like a slinky. You just have loops and loops and loops and loops. And using Ampere's law, we can actually estimate the magnetic field inside and, of course, outside the solenoid. Right? Now, the trick here is, like I said, we can approximate the magnetic field for this. The closer these loops are bound together, the more accurate your solution will be. The farther out they are, the not so accurate they'll be. So the idealized case we look at almost all the time is when the loops are almost right next to each other. They're touching in contact. Now, if I was to take a cross section of these solenoids, or the solenoid, I have loops like this, right? Loops on top, loops on the bottom, right? So depending on how you're looking at it, let's say I have current coming out of here, and let's say I have current going in. So if I'm looking at this, let's say my current is going through this way. So up here I have current coming out, going there, going in. So that's the cross section I'm looking at. So all the way up here I have current going into this, and all the way down here I have current coming out. Right? What's reversed? Yeah, it depends on how you look at the cross section, but the cross section I'm defining to be is currents coming out on top and going in at the bottom. Right? Now let's take one loop. Right? Let's erase all the other loops. Let's look at one loop. Now obviously I have current coming out, current going in, so it's going to have a, sorry, I didn't hear it. Someone said magnetic field? Magnetic field, yeah, all right. So it's going to have a magnetic field that you can see through here, and we actually looked at a diagram for this last time, right? This is what is this? Essentially like a dipole. So what is this going to look like? I have current over here, it's coming out, So my magnetic field is going to look something like this, with this being the direction of travel, right? Now, same thing for this, but the other side. So I have magnetic field, but it's the direction is going the other way. So going in, something like that, right? So I have basically on both sides, I have field lines going out, diverging out this way, the divergent ones, right? Right. So these two, that's essentially more or less how it looks like. And obviously, my diagram there sucks. But for those of you who printed out the notes, you'll see on figure 13 that that's what it looks like. So now let's look at a like a contour of these things. So I have a better drawn diagram in my notes, but let's see if I can reproduce it properly. So I have something like this. So I have a plane here, and I have basically, so it's the cross section I'm looking at is something like this. I have a plane there, plane here. And this is my x-axis. This is my z-axis, and this is my y-axis. Right. So when I look at the field lines here, I mean, of course, if current is going through this way, right? If a current is going through this way, I would get field lines that are going around in this form, right? And same thing on the bottom. I'd get field lines going the other direction. So it'd go down this way and somewhere inside. So that's sort of like like a contour of what I can expect from one of these solenoids. Now let's calculate some stuff. So if I was to have by the way, this is a solenoid for those of you who were wondering. Now, if I take a solenoid and the length for this, let's say, is L, I want to find the magnetic field here. So I know that magnetic field, given all the diagrams, if my current is going through this way, that I can expect my magnetic field to come out like this, right? At least inside. What do you think is the magnetic field outside a solenoid? Big as in? Right, it's a loop, but it's basically negligible. Why is that still on? Right, so the field outside a solenoid, it's almost negligible, and we'll discuss why that is. I mean, I was expecting a different solenoid here when I requested a solenoid for demo, but we'll see if we can figure it out. Yes.
So when you say it's negligible, are we basically stating that the loops that are going to be outside of it are just going to cancel each other out? In a sense, but not completely.
Yeah, and mathematically speaking, yeah, you can think of it's something like that. But for instance, if I was to ask, what is the magnetic field up here? Then obviously, whatever field lines you have over there are closer than what you have over here. So it doesn't quite work out the same, but you'll see that it's basically negligible on the outside. And we actually assume that when we make our calculations. So yeah, now we have to, like I said, I want to calculate the magnetic field of this. I want to find out what that B is. So how would I go about doing that? Did I hear Ampere's law out there? Right, Ampere's law. Use Ampere's law. Okay. You guys have to indulge me sometimes. It's kind of boring talking here for an hour and a half. So closed loop, B dot dl equals mu naught I and closed or penetrating. Now, Again, this is not the actual proper Ampere's law, as we'll find out later. We have to make some corrections. But okay, we take that. Now, what's the? I wrote down some 3 basic rules. What's the first thing I need to do? I need to define a loop. What's the second thing I need to do? Choose a surface. Okay, what's the third thing I need to do? Choose direction of travel. Okay, so what loop shall I pick here? What loop do you think is appropriate here? What? I heard a rectangle. No, no one said a rectangle? All right, well, it is a rectangle. So let me redraw this. Well, yeah, let me redraw this real quick. Right, so we have right, so this is our cross section of that solenoid, and I'm saying that we have a magnetic field going out this way, right? Now, the loop I'm proposing we use is something like this. Right, so I want to use that loop. Now, the way we integrate these rectangle type loops is we break them up into segments, as I mentioned earlier, and then we integrate them. Yes? So let me see. Let me think about this. For my field is going, my current's going there. So it's going there. Yeah, I guess so. You're right. Is it right? So you have field going this way. So yeah, it would be going the other way. All right. So my magnetic field is going this way. So just ignore the direction on the in the notes. It's making this at 4 in the morning, so not exactly enough time to think. All right. So I have my field going this way. So I want to obviously divide this up into parts. I have 1, 2, 3, and 4. Right. I have 4 different segments here. Right. Now over here, as I mentioned earlier, this segment here, b equals 0. Right? So if b equals 0, what is my b dot dl equals there? 0. Right? So there's no contribution from that. So for loop 2, or not a loop 2, but for segment 2, b dot dl here equals 0. Although, if I'm my dl I'm saying is this way, it's in the same direction, it's still 0. What about loop 1? What's my integral of b dot dl? 0, because it's perpendicular. Yes, precisely. Because my dl, my direction of dl would be something like this. My direction of b is this way. So they're both perpendicular, right? My magnetic field is 90 degrees from that segment. So therefore it has no contribution. I mean, even though at this particular point inside the solenoid, you would have some magnetic field that the segment experiences, it's still 0 because it's perpendicular. That's 0. What about loop 3? 0 by the same logic, right? Because magnetic field is perpendicular to my direction of travel, it's going to be 0. right? Okay, what about loop 4? For loop 4, or not loop 4, but segment 4, we have, let's go the other way. Let's go this way. So the other ones aren't affected because they're all 0, but this one just makes my life a little bit easier because my DL is in the same direction as my B, so I get B dot DL. Well, overall it's going to be B dot DL equals mu enclosed, mu naught I enclosed, and this loop, this integral will give me integral of B dot DL. It's going to be equal to B DL is basically the segment of this length. I forgot to mention this. The width of this is length small l. Let's call it. Right. So I'm integrating over DL. It's going to be BL or BDL. I integrate over from 0 to L. I get BL equals mu naught I enclosed. Right, or penetrator, however you want to look at it. Now, where's the current in this loop coming from? It's coming from these top portion of the solenoid, right? So they're penetrating through, right? They're completely, all these, each individual ones are penetrating through. So what do you think is going to be my I penetrator or I enclosed here? Not exactly. You're right. I mean, number of loops does come into play, but it's not directly the number of loops times that. What else do I need? What's that? No, not for this. Yes, I would need the turns per unit length, right? So if this is my unit length, and I need to look at the number of turns in that. I mean, I have the total length of the solenoid, right? That comes into play, but I also need because I'm looking at basically a small fraction of that here for this part where I'm calculating it, and I need to later generalize for the whole thing. I need to look at the turns per unit length here. So I would get something to the effect of BL here equals mu naught I, right, times small l times n over big L, right? So this right here gives me the turns per length, right? To have a total length for the solenoid of big L, and I have a certain number of turns in that solenoid, certain number of loops in that solenoid, right? So that gives me the, I guess if you want, loop density, if you want to look at it that way, and I multiply it by whatever I'm looking at here for that length. However, you may say, okay, this is just some arbitrarily picked out length. Now, how can that possibly be part of the solution? Well, this is when we just cancel it out, and it's gone. So the magnetic field I end up with is B equals mu naught I n over L. Right? Yes, the capital L is the initial length of the entire solenoid. Now, this approximation essentially holds as long as this this length is a lot larger than the radius of the solenoid. So the radius of the turns. So this has some radius r. As long as the length, the big length you're looking at, is substantially larger than that radius, you can make this approximation. Right? All right, so how about we take a 5-minute break, and we'll meet back here and finish it up, look at some demos, and if we have time, we'll get into induction, or let you guys go. So a question that was brought up is, why is this sort of like a loops per unit length or loop density as opposed to just loops? Because if I have a certain number of loops, then you may think it's okay, reasonable to say if I have 10 loops, it's 10 times this magnetic field, right? It's not the case because, as I was saying, if I have a really long solenoid, let's say the solenoid goes from this room 203 to blocker, right? I can't realistically feel the effects of that first loop, right? If I'm over there, I can't feel the effects of the loop in this room, right? No matter how tightly wound they are. So obviously we know that it cannot be an aggregate effect of all those loops combined. Right? So an more appropriate way to think would be to think about it is if we were to stack all the loops on top of each other, right? And would have a magnetic field that would be generated by it, then that sort of gives us loops per unit length. If I have a certain amount of length and a certain amount of loops, then I would have a loops per unit length, and that gives us a closer approximation to what the magnetic field of a solenoid is. So I mean, it simply cannot be just the total number of loops times the magnetic field, because you can't have that. If you think about it, it just won't work that way. So it's more of the loop density. If it's really highly dense, then you have a large number of loops per unit length, then yeah, this magnetic field is going to be pretty much those loops times that. But if it's sparsely spaced, then if the loop density is smaller, then you'd have a smaller magnetic field. So does that make sense? Right. So let's put some numbers to this. So let's look at a solenoid with 2,800 turns. Let's look at it this way. So let's say I have N is 2,800 turns, right? And the length of the solenoid is 0.6 meters. So it's a really small length, relatively speaking, but a lot of turns. And they don't have to be right next to each other. I mean, yeah, they do, but they can also be on top of each other. So it's just a bunch of loops packed on top of each other or next to each other. And let's say the current I want to pass through the solenoid. Let's say that this is the solenoid. Obviously, this doesn't have 2,800 loops, not even 0.6 of a meter, but hypothetically, let's assume that. And this is my power supply. Let's say I'm passing through 4.5 amperes. So my current going in is 4.5 amperes. So when I calculate this, I would have mu naught is what? 4 pi times 10 to the negative 7, right? Times 2,800 loops, times I have the current, that's 4.5 amperes, over the length is 0.6 meters. The whole thing obviously is magnetic field. The unit is Tesla. Obviously this has some units, and it will cancel everything out and give me the Tesla I need. But so this is approximately 0.026 Tesla. So it's approximately 260 Gauss. Right? So yeah, it's more or less appropriate. Now, solenoids are interesting because there are a lot of applications that can be attributed to it. Right? They're especially useful when you need to have controlled movement of a small controlled movement in a restricted area. Now, I'm sure there are some motorheads among you. Are there any? Car fanatics? Right? All right, that was one or two. Okay, so the most widely used application in cars is for starter motors. So what do you have? You have a solenoid in the starter motor. You put the key in the ignition, right? You turn it on, you try to crank it. I mean, when you crank it, the starter goes on, right? But a small current goes to the solenoid, which then operates basically connectors, connects it to something else, and then that passes larger current from the battery, and then operates the starter motor, and you get the engine cranks over. Right? So that's one of the biggest uses. Another use that I had to deal with, I mean, it's also there. So for those of you in the audience that are BMW fans, the BMW uses something called Vanos system. Right? So many car manufacturers have something similar to that. You have Honda has their VTEC, Toyota has VVTi, Ford came up with something similar. BMW's variation is Vanos, Porsche has a VarioCam. So what this essentially does is it's a variable valve timing system. So when you have higher engine speeds, it switches to a different higher speed valves. And when you have lower engine speeds, it switches to lower speed valves. And these days they're getting smarter. They do them intelligently, not necessarily based on the engine speed and all that. So to make the car more efficient, and also when you need it more powerful. Now, obviously you have variable valves. So what happens is, in this part at least, you have the camshaft that sort of moves about a little bit. So they use solenoids there to sort of move the camshaft where they want it to operate the different set of valves. Now, the BMW system also uses solenoids to maintain their intake and exhaust valves. Right? So if you want to close a valve, open a different valve, and all that, they use solenoids. And so in my dad's car, one of those solenoids got stuck. It got oil that leaked through and got stuck, and it was an absolute pain to get that fixed up. So the way these guys operate is, we looked at the standard solenoid, right? So you have, if I look at a different cross section of it, I got, let's say loops are packed on top, and in here is just where the magnetic field would be. So the way it would work is, if I have that loop in here, it produces a magnetic field in there. Now you put some sort of metal in there, either iron or something else that responds to that magnetic field and moves about. So you don't want to just if you create a magnetic field, it would probably just pull it because of the magnetic field, and it would stay there. So the way they come across that is they put a spring on top, so it sort of is under some tension. Magnetic field would push it, and then when there's no current passing through, there's no magnetic field, it would go back to its original position. And it's not just for cars. You have solenoids that operate pressure valves. Any one of you in the biomedical engineering, you probably deal if you're dealing with some sort of dialysis machine to control the valves of blood coming in and all that. You have solenoids that operate those valves. Even the normal pipes for the pressure and all that, high pressure, low pressure pipes, for the inlets and all the outlets, you have solenoid that stick there, and then you have current going through them, pulls up the valve, and you have whatever fluid you want to flow through will flow through. So there's plenty of uses, and people obviously get more creative and come up with more elaborate technologies for this. So these are rather interesting stuff. Now let's look at these final two demos, and then we can get out of here. So this one is essentially going back to what we went over on Wednesday, right? We said that if you have a certain current that goes through, it generates a magnetic field, right? Like I said, seeing is believing, so I want you guys to see this. Over here we have a compass needle. And we have a thin wire here, and I have just some batteries here. So batteries have some, their source of EMF, right? The wire will have some resistance, which means that there will be some current passing through the wire, right? And we can calculate what that is. I have 4 of these, so that's 6 volts, right? This wire obviously has some resistance, so based on how conductive the wire is, you'd have some current going through. All right, so when I touch this, do you guys see it? Does everyone see it? So the compass needle moves about. So it's clearly a magnetic field that's created by this. See that? Take it out, it goes back to normal. All right. So that's the first one. The second one I wanted to show you guys is, well, this is not what I was expecting when I requested solenoid. I was hoping for something like this, a small solenoid where I can sprinkle some iron filings and show you, hey, look, there's no field on the top. Well, I can't really do that with this one, so I was going to improvise here. So what I'll do is I want to show you guys that there is a magnetic field in here. So I'll take that compass needle, put it through in the middle, and I'm expecting it to sort of move about. I haven't done this yet, so hopefully this works. So it's on. Crank up the voltage. Let's say I want to put in about 5 amperes there going through, right? So it's 5 amperes going through this loop. So I should expect a change in the magnetic field. Right? Take it out, goes away. So let's stabilize. Let's put it in again. Take it out, stabilize again. So there you go. There is a certain magnetic field inside that. All right. So actually, let's crank it up more and see if we get anywhere with it. Oh yeah. Oh yeah. Look at that. Cool. Good stuff. All right. So I think let's end it there. We're running 10 minutes early. We'll start induction on Monday.